This talk is going to be about a tool that I've been working on called Androsia. And it is a tool for securing in-memory application data, specifically meant for Android applications. So let me give you a brief overview of the tool and what it is supposed to do. This tool is a static code analyzer which goes through your code and tracks object instantiations. And once it spots some objects instantiations, it tracks the object so that it can figure out what is the last use of that object. And once the tool figures out the last use of that object, it can instrument code in the application so that its memory content gets cleared. How is that useful? So let's just assume that that object contained sensitive information, and you don't want the code to maintain that sensitive information throughout the lifetime of your application. You would like to clear that memory as soon as it is last used in the code. So this is what our tool is mainly about. Let me go through a quick introduction about myself. I'm Samit Anwar. I work for the product security team at Citrix R&D. I'm a web and mobile application security enthusiast. I've spoken at a bunch of conferences, including IEEE Services, ACM MobileSoft, IEEE CloudCom, and CoCon. So you can reach me via my email, samit.anwar@gmail.com if you would like. You can tweet at samitanwar1 as well. So moving on to the agenda for the talk, I'll be speaking about the main takeaway from the presentation, what motivated me to do this work, why we are doing what we are doing, and a brief background about the framework that this tool is written on. I'll quickly show you a demo after the background, and then we'll dive into the approach that we take in order to analyze the code. And that'll be a little bit technical, so be prepared for it. And the work in progress, yeah. So the main takeaway, let me explain it via the help of this diagram. Let's just assume that 1 to 10 are the statements in your code. And at number 3, you see that a variable x is being defined. And let's just assume that the x is being initialized with the object initialization. And at statement 5, it is being used. So the idea from this diagram is that before statement 3, x never existed. So we can say that x was dead between 1 and 3 statement. However, x was initialized at statement 3, and it is being used as statement 5. So we can say that it is live from the time span from the statement 3 until 5. Then x is again redefined or reinitialized at statement 7, and then used at statement 8. So between 5 and 7, there is no use of the variable x. So we can safely say that the variable x is dead between 5 and 7. And we can also say that a variable x is live between 7 and 8. And it is dead after 8. So that's the definition of liveness of a variable. What we're going to achieve out of this tool is we're going to determine the last use of objects at a whole program level. This diagram was basically a single flow within a specific method, you can say. So we need to do this at a whole program level. We need to figure out points like statement 5 and statement 8 at a whole program level. And what we're going to use is a summary-based interprocedural data flow analysis. Data flow analysis, if folks around here are not aware, is basically a static flow analysis, but it's not just about pattern matching. It's about propagating data flow facts throughout the program. So every statement contributes some information to your code, and what you need is that you need to propagate the data flow one statement at a time whenever the next statement is executing. But again, this is a static code analysis, so we are not executing any statement at all, but we're just propagating information that we can gather from one statement to the other, and using that information to determine liveness at a whole program level. So devs want to ensure that objects memory gets cleared. This comes after their first priority, which is to make the code work. But nevertheless, they want to do that. And the myth is that the garbage collector will handle it. However, that's not true because the scope of garbage collector is very limited. And as you all know, the garbage collector works on the mark and sweep algorithm. Basically, it starts with the GC roots, which are the garbage collection roots, which are special objects like the main thread in the program, or the variables allocated on the main thread, or your static variables of your main class. And it goes on doing a depth first search and marking all the objects that are reachable through references. And once it marks all the objects that are reachable, it skips to this sweep phase, wherein it will go through all the objects in the heap memory and see which all objects are not marked. And the unmarked objects will be reclaimed. So what I'm trying to come to is that developers might forget some references, like the one shown in the oval. And these objects might contain sensitive information, which will eventually be overlooked by the garbage collector and will not be collected. So your sensitive information will remain on the heap memory throughout the lifetime of the application until your Android operating system hits a resource constraint, and then it will invoke the garbage collector to collect these objects. Even then, there is no guarantee that these objects will be overwritten. The space will be available for being overwritten, but there's no guarantee that your sensitive information will be overwritten. So this is precisely the problem we are trying to tackle. We'll be explicitly going to clear the memory content of the objects when it is last used. So in our tool right now, we are focusing on string builder objects, but it is very straightforward to extend this tool to any other kind of objects. So unused but reachable string builder objects may contain sensitive information, and a heap dump will reveal that sensitive information. So don't just rely on the garbage collector to clear sensitive content, but destroy by overwriting all critical data. So Java security package has some classes which provide, like the keystore.password protection class, which provides a destroy API. I hope it's clear. So it provides a destroy API. But again, the onus of calling this API is up to the developer. He might even forget to call this API, or he might call it at a stage very late in your program. So that's what we are trying to do. We are automating this process where we'll figure out this is the last point where your object is used. I'm going to instrument the code, or there are two modes of our tool, where in one mode we can instrument the code for you, or in the second mode, we can just provide feedback to the developers that this is the point where you need to call the destroy API, or you need to destroy the object. This is a snapshot from the Eclipse memory analyzer tool, which basically tells you that there is a static field called static secret, and it has a password string inside it. And this is a snapshot of the heap taken before optimization of the code. And once we instrument the code, at the same point, we take a snapshot again, and you'll see that the password is not anymore present. So coming on to the background, to write this tool, we have used a framework called Suit. Suit is a Java bytecode analysis framework. And one of the main features of this tool is that it has an intermediate representation called Jimple. Jimple is a cross between Java high-level language and the bytecode. But it is similar to Java, and it's simpler. So it doesn't have the nested structures that are present in Java. So it's Java plus simple, so it's Jimple. And it is more or less a 3-address code, which looks something like this. So what I mean by 3-address code is that at any particular statement, like if we take the example of the if statement here, there are not more than 3 operands in one line of code. One is R1, the second one is null, and the third one is label 0. Right? So that's how Jimple looks like. Also, Jimple is beneficial because you just have 16 or different kind of statements to deal with as compared to 200 or something opcodes when it comes to Dalvik bytecode. Moreover, Jimple preserves the typing information of variables as well, like integer or any sort of objects, which is not present in the opcodes, which is not present in the Dalvik bytecode, I'm sorry. Yeah. So suit also allows you to perform intra-procedural or inter-procedural data flow analysis. What that means is you can perform the analysis within a method, or you can perform the analysis at a whole program level, wherein once you analyze one particular method, you pass a summary of that method to other methods so that they can use the information that you've already analyzed. Until like 2 years before, Suit was missing a Dalvik to Jimple transformation module. But that work has been completed, and the module is called Dexpler, which basically disassembles your Dalvik bytecode to Jimple. So it just plugs into this Suit workflow where you had support for Java source code, Scala, and now there's Dalvik as well. So you can convert the Dalvik bytecode into Jimple 3-address intermediate representation, and then you can generate you can analyze your code and then generate the Dex file or the Jimple files again. So another tool that we had plugged into our tool is called FlowDroid, and there's a very specific purpose we use this tool for, which is to generate a dummy main method. Unlike Java applications, Android applications do not have a main method. And FlowDroid generates a dummy main method for you. It basically simulates calls to Android lifecycle methods like onCreate, onStop, onPause, onStart. And it also simulates calls to user-driven events, callbacks meant for user-driven events like on key pressed, on press, on click. So those kind of events. And let me just show you. So this is how the dummy main method looks like. It'll basically, this is a call graph for the entire program after we run FlowDroid on it. There'll be a dummy main method which will invoke all the other methods like onCreateView, which already exist in your application, or onCreate method. So this is needed because in order to perform your data flow analysis, you need a call graph. And you need a starting point from where you need to start flowing your data from. So this will do exactly that, and it will provide you the call graph with a single entry point. So just to give you a design overview, a developer or a user of an application can share the source code or the APK with us, and we can pack the APK, convert it into, fetch the Dex code from it, convert it into Jimple code, and perform the analysis and instrument the code in Jimple code, and then package it back to Dalvik bytecode and create an APK with the resources packaged along with it, and send it back to the developer or user. So string builder objects can exist in multiple scopes. What I mean by that is that they can exist as local variables in a method, wherein their scope is limited to this particular method only. Like here you see XYZ are being instantiated, like XYZ are being reference variables pointing to string builder objects. SB stands for string builder. So you have a secret password that is being assigned to X and Y. But the use of these variables is limited to the method foo, and they don't have any other use anywhere other than this. So they can exist as local variables in a method, or they can exist as static fields of a class. And there's a drastic difference between the scope here, because as soon as you allocate an object to a variable which is a static field of a class, the scope becomes the entire scope of the program. And any other class can access that particular variable using the class name. So here I have a bar method being invoked, which is trying to use X using the class name myClass. So there's a difference between the scope of the string builder object. There's another scope where they can exist, which is like an instance field. Here the variable X is an instance field for my instance field SB class. And now the scope of this particular field is limited to the scope of object of the class encapsulating it, which is my instance field SB. So whenever obj, which is the object that has been instantiated for my instance field SB class, goes out of scope, you cannot access X anymore. So our tool caters to all these cases, and with that, let me quickly get to a demo here. I'll introduce the code. There is a user class which defines a static string builder field, which is called static secret. And then there is the main activity class with the onCreate method, which instantiates the string builder object with value password. And in the check static class, we are calling the useStatic field from the onCreate method. And that useStatic field basically is using the static secret variable. So there's the use, and then we are calling bar again. So bar, inside bar, we are using the static secret once more. So if the tool had to run on this piece of code and figure out where the last use of static secret is happening, it's very obvious, right? It's right here. There's no further use of the static secret field. So you can instrument the code right after this statement and clear the content of static secrets object. However, that's not how simple life always is. There can be loops as well. And with static fields, the problem is that if the bar method is in a loop, you cannot instrument the code after the println statement of static secret inside bar. Because once you reset, in the next iteration of the loop, you will be accessing the resetted value rather than the original value, which will break the logic of your program. So you need to take care of all these situations. So this is the same code. The main activity class basically instantiating the string builder with password, and then you're calling the useStatic method, your useStatic field method of the checkStatic class. So inside useStatic field, there is a use of the static secret, and then we're calling method bar, which again uses that static secret. And I've, for convenience, I've added a couple of more println statements so that it becomes obvious where the code is being instrumented. So right now, if you'll see, the code should be instrumented after the println statement for static secret, which is just below the println statement for hello, just above the println statement for hello. So let's just run the tool on this example. So all this method, this is the dummy main method I was talking about. So suit generates, the floater generates this dummy main method for you. It's actually in Zimple, so we don't need to really go through it right now. And the output format for the current configuration for the tool is set to Zimple, so that we need to see where the code is getting instrumented. Alternatively, we can set the output format as DEX, which will give you an APK file as an output. So inside the bar method, you'll see that there's a println statement for hello in line number 38, which is at the bottom of the screen. And the code has been instrumented just before this in line number 36, 34, 32, and 30. So what we are doing essentially is that getting a reference to the static secret, trying to figure out the length of the static secret by calling the length API, and then invoking the delete method from 0 to length of that static secret. So we are clearing its memory content. And this is actually the right point where the code should have been instrumented, and that's what has happened. So if I had introduced a loop inside the bar method, like this one, just uncommented an existing loop, the instrumentation point would change, and now it would be right before the by statement, the print line statement for by. Because it's a static field, right? You can't reset it within the loop, otherwise in the next iteration, you're going to use the resetted value. Yeah. So this time, the instrumentation has happened just before the print line statement for by. So as you can see that in the Jimple code, all the loops are converted to go to and label statements. So yes, here you can see if I not less than 50, go to label 2. So your loop body will be actually present in label 2. And if the loop's condition is not true, you will be executing the code from line number 29 to 39. And as you can see, the instrumentation has happened just before the print line statement for by, which is right here. So similarly, we could have loop around the bar method call, and again the instrumentation would be happening inside the useStatic field method before it returns. So you get the idea, right? I'll probably skip this portion and then give you another demo on this one. Yeah, this. Yeah, so now what I'm going to do is that I'm going to call useStatic field inside a loop. And once I do that, the instrumentation point should get updated. It shouldn't happen inside the useStatic field, but it should just happen right before the setPassword method call. And as you can see, again, from line number 74 to 78, you have the instrumented code. And that is right before the API called for setPassword. So what I'm going to do next is introduce another use of the static secret string after the setSecret method call, just outputting it. So now that the use has been updated, the resetting should not happen before setPassword. Instead, it should happen right after the system.out.println statement. So yeah, here's my println statement, and this is at line number 82 is the println statement, and I'm instrumenting code after that, just before the onCreate method returns. So the tool is smart enough to decide where the instrumentation should exactly happen, and it can inform the developers about it, or it can go ahead and instrument the code like what is happening right now. So we've seen what the tool does, but we still don't know how it is happening. And let me just dive into that. So in every line of code, you have a lot of information. And if I had to be pedantic about it, in data flow analysis community, we call them data flow facts. So, but we are interested in a specific data, which is the liveness data of variables. And the next few slides are going to cover how we'll formally define live variable analysis, how are we going to compute summary for every method, which will tell us information about a method. Basically, it will tell you what variables are defined in that method and at what statement inside that method they are last used. So the summary will look something like this. Every method will have its own summary. So summary of foo will tell you that there is a variable x whose last use is happening in this particular blue statement, if y.length is less than x.length. So the summary would look something like this. And we'll do this for all variables inside the method and all methods in the entire application. How do we generate the summary? We compute something known as def and use set, which is a definition and use set. And we are going to use the definition and use set to compute live variable entry and exit set for every statement. Even the def and use sets are computed for every statement. And we're going to compute LV entry and exit for every statement using def use sets. And once we have the LV entry and exit sets, we're going to use that to infer the summary for every method. Basically, the summary will contain last usage point for all local variables and static field references within the method. And then we'll see how can we use the summaries computed for one method to compute the last usage point of that static field reference in the whole program. So let's just define live variable analysis. Live variable analysis determines for each statement which variables must have a subsequent use before they get redefined. This is exactly what we saw in the diagram which I showed you on the initial slide. And if we had to figure out the live variable, so the last usage point of a variable can be equivalently called the last statement where that variable was live. And in this particular code, if you see, the last usage point of variable x is this blue statement, y.length is less than x.length. It is not being used beyond this statement. It is being defined here again, but it's not being used. So, yeah. And similarly for y, the last use is happening at statement 5 and statement 6. And for z, similarly, we have the last usage here. So the last usage point of a variable is the last statement where the variable was live. The variable is live here because it is being used, but it's not being used ahead in the program, so it's not live anymore. This is an if-else condition, so either this statement will execute or either the 6th statement will execute. So one of them will execute. That's why both of them are the last usage point. So now we're going to do the step 1, where we're going to compute the def use set for the same code. Def set will contain all the variables that are defined in that statement, and the use set will contain all the variables that are used in that statement. And this is how the def and use sets will look like. So for the last statement, we'll have x as the def in the def set and z in the use set, and so on. Pretty intuitive. So once we have the def and use set, we are going to compute the live variable sets for every statement. And the way we do it is using a backward flow analysis. So what I mean by that is that the live variable analysis sets will be computed in the reverse order of program execution. So we're going to compute LV exit of the last statement first, which will be phi because there's no variable which will be used after the last statement. So we can safely assume that the live variable exit set for 6th statement will be phi. And then we're going to compute LV entry 6, then so on we'll go up in the program reverse program execution order. And whenever we reach a branch condition, we're going to take a union over the entry sets of the successors. So we're going to take the union over LV entry 3 and LV entry 4 and pass it on to LV exit 2. So that's how the data flow facts flow. If I had to express them as equations, it will be something like this. This is exactly the same thing which I mentioned over the previous examples. If the statement is the last statement of the body, then the LV exit set will be phi. Otherwise, we'll take a union over the successors of LV entry. If we take a union over the successors, we'll take a union over the LV entry sets of the successors. Sorry. And then to compute the LV entry set, we are going to take LV exit minus def union use, which we have already computed. So as I said, LV exit of the last statement is always 5. So we have that in the table there, right besides the 7 number. And now we are going to compute LV entry. So LV entry will be LV exit minus def union use. So that will be 5 minus x union z, which will be z. And so on, we can do this for every statement. And what we'll notice here is that in the live variable entry and exit columns of the table, if a variable disappears from the entry to the exit set, that means that was the last use of that variable. So as you can see in statement number 5 and 6, y is disappearing from the entry to exit set. So we can say that 5 and 6 are the last usage point of variable y. Whereas for z, the last usage point is 7 statement because the variable is disappearing again. And for x, it will be 4, which is the if condition. So that's how we basically automate this live variable detection for our purpose. And we store it in a summary. Every variable along with the last usage point of that variable. Every static field reference along with the last usage point of that static field reference. So this gets even more complicated because you might have different variables pointing to the same object, which are generally known as aliases. So it's not just one static field reference you have to track, it's all the aliases that you need to track. And for that, you need something known as a alias analysis or a points to analysis. So once we've computed the summary, we need to use that summary because there could be a method foo calling bar and bar calling baz. And once we've computed summary for every method individually, we need to use that summary at a whole program level by passing that information to other methods. So here we have summaries for all the methods. As you can see, foo is calling bar is calling baz. And the static field references are used at B5 and C4. So in the summary, you have that information already. So what we are going to do is again run our tool on this program, and as I said, it goes in the reverse topological order of method execution. So baz will be analyzed first, and then bar, and then foo. And the analysis flows backwards. So the last statement of baz will be analyzed first. And then we'll keep going in the reverse order of program execution. So we'll analyze C6, C5, then C4, and we'll see that SFR is being used here. So we'll put SFR in the entry set for C4, and that information needs to be updated in a whole program level data structure where we want to track the last use of the static field reference. Right now, we have just seen that the static field reference was last used at C4. So we are going to update that red data structure with the method name and the static field reference name and the statement. Once we keep on going, we'll hit a point where we're analyzing B5, and we'll put it in the entry set. Now, once we reach B3, we see that baz was called there. And what we are going to do is pull in the summary for baz and see whether we want to update the red data structure or not. Since we can see that we are using the static field reference at B5, which is coming later in the sequence after baz gets called, so we need to update that data structure because SFR is being used last at B5 and not really last in the baz method. So we need to update that data structure, and we'll change it to bar SFR B5 because SFR is last being used at B5 in bar method. And so on. We reach A3, wherein we see that the LV exit set has only 5 in it. So we don't really need to update the data structure because SFR was not being used in foo method after bar was called. Yeah. So that completes the analysis. So at the end, what we achieve is that we get the last usage point of the static field reference SFR, which is at B5 in the bar method. So just a checklist, we've covered live variable analysis, how the summary looks like, how do we compute the summary using def use set, how do we compute LV entry exit sets for using the def use sets, and finally, how do we use the summaries to compute the last usage point of a static field reference at a whole program level. So there are some work items that are ongoing. One is the instance field approach. I'm like 90% through it. So the approach differs from the rest of the analysis in terms of the tracking of the objects. We are not tracking string builder objects directly here, but we track the object of classes encapsulating the string builder instance fields. So as you can see that we mark all classes which are string builder instance fields, find their object instances, and track the object instances rather than tracking the string builder fields themselves. And as you know that instance fields can have access modifiers specified to them, so we can't just reset them from anywhere. We need to reset them through a method belonging to that class itself. So we add reset methods to the specific class that we are tracking. Like here we have the instance field X, which is private. So we'll be adding a reset method inside the myInstanceField SB class, which will be responsible for resetting the variable X. And instead of tracking the string builder X, we'll be tracking OBJ, which is the instance of the class myInstanceField SB. So we're also in the process of developing a test suite for the tool. We plan to integrate into the CI/CD model and almost there with the documentation. And the GitHub repo can be found here. The code is private. As of now, it's going through the legal process because I work for Citrix, so I need to take the prior permission before making it open source. So it's going through that process right now, but I hope it gets through. So yeah, that's the talk. Yeah, thank you. Some reference to go through. Yeah.